You'd have made your life easier.
Yeah.
Okay. So, glucose 1-phosphate. If we draw glucose 1-phosphate, I'll move over here. If we draw glucose 1-phosphate and we try to draw it in the chair conformation, right? These 6-membered rings try to make a chair. Now, I'm going to draw glucose first. Because if you remember when we talked about this last semester, when it goes into the chair, let's see if I can do this without messing it up. I'm going to go back this way. All right, if we do that, then this OH ends up, right, this is carbon 2, that ends up equatorial, the hydrogen ends up being axial. Right? This OH ends up being equatorial. The hydrogen ends up being axial. Right? When we lift this up, this OH ends up being equatorial. Right? This hydrogen ends up axial, and this group with the OH ends up being equatorial. Right? But that's going to put, if it's the alpha form, which this is, it's going to put this hydroxyl axial. So, remember, that was the reason why the alpha form was slightly less stable than the beta form of the cyclic glucose molecule. Because in the beta form, you get this hydroxyl equatorial as well. And so you get all your bulky groups equatorial, which is what we said was the, right, that made the beta form more stable than the alpha form. Well, what happens if here at carbon 1, still alpha, instead of there being a hydroxyl there, we put a bulky phosphate group there. Right? What does that do to this group? Right? We created a lot more, what is it, 1,3 diaxial interactions, unfavorable 1,3 diaxial interactions. Right? So either this ring is going to try to flip to relieve those 1,3 diaxial interactions. But if the ring flips to relieve these 1,3 diaxial interactions, what happens to the interactions of all those other groups? What?
They become greater.
Right. Right. The interaction, everything that right now is stable because it is equatorial gets forced to be axial, and those then have unfavorable interactions.
Is that hydroxyl on like carbon 6, I think it is? Is that?
This one?
Yeah.
So this is going like out and away, and the break means it's behind this one.
Oh, I see now.
Right?
Okay.
It's sticking back there.
So it's equatorial, though, right?
Right. It's still
Okay, 'cause the
equatorial.
hydrogen-
Right. That is this carbon.
Yep.
Right.
Okay.
So it's back away. Okay? Does that make sense? So the only justification I can come up with for why glucose 1-phosphate is considered so much higher energy than glucose 6-phosphate, when they both have, well, how is that phosphate connected to both of them? Oh, black hands. What kind of linkage puts the phosphate on both those molecules? Well, we got ether, ester, and hydride. Pick one. No, try again. No, okay. Ester.
Yes.
Yeah, it's an ester. Try to be forceful. So, it's an ester. So, the only justification I can come up with, who was it that came and asked me this question yesterday in my office? It was Kyle, right? The only justification I can come up with for why glucose 1-phosphate as a phosphoester is so much higher energy than these other phosphoesters is this one. That by making this bulky group here, you create, let's see, you create not torsional strain, you create what? Steric strain. You create steric strain that raises the energy of that molecule. Because either this is axial and doesn't like it, or those things are axial and don't like it, or to try to get part of these to stay in some semblance of a low energy environment, this might get forced into a boat structure, right, where these can stay equatorial on this side, but that's equatorial on that side, but the boat structure creates torsional strain, right? And so that's the only, in thinking about your question that you asked me yesterday, Kyle, this is the best answer I could come up with, yeah.
So the glucose 6 and 3-phosphate, they're equatorial?
Or is it just far enough away? It's
Yeah,
carbon
right, the
6.
glucose 6-phosphate, the phosphate group would be over here, right? Not only equatorial, but equatorial held way, an extra carbon away from the ring. Right? Does that make sense? That's as good an answer as I can come up with. Is that a satisfactory answer to your question?
Yes.
His question was because right, we've got this, right? The pyrophosphate on this list, the pyrophosphate is actually on this list lower energy than the glucose 1-phosphate. So an anhydride bond is lower energy than an ester bond, which normally would not make sense.
So why is the fructose one above glucose?
They're the same.
They're the same.
Oh, I didn't realize that.
Right. I
Okay.
mean, that I think
That's why.
I think alphabetical order one there.
Fair enough.
They're the same. And the glycerol 3-phosphate, which is a smaller ester that doesn't have to worry about any of those ring strain issues, is the lowest energy of all. Okay? So, as we are considering these, I think you can spin that around and look at the screen again. Right? There we go. I drew all those structures, right? So we can look at them. So we talked about phosphoenolpyruvate on Wednesday, right? What kind of linkage is linking the phosphate to the molecule? What kind of linkage is that? Elizabeth? Are you sure?
No.
Are you sure it's not an anhydride or an ether?
I think it's ester.
It's an ester. But if it's an ester, why is it the highest energy molecule on the list? Right. The product of the simple hydrolysis is that enolpyruvate, and is the energetically favorable tautomerism of the enolpyruvate that ultimately makes this a high energy molecule. Right? I don't know, can I say what again? What did I just say? I don't know. You guys think I pay attention to myself when I'm talking. You keep asking me to repeat myself. I'm really not paying attention. What did I say?
It's the stable product of the atomization that makes it.
Right. It's not the hydrolysis that makes this high energy, because we're hydrolyzing an ester. The product of that hydrolysis is the enolpyruvate that we drew on Wednesday, right? And it's the tautomerism of the enolpyruvate product that ultimately is what releases the energy in this process. Okay? So that one we talked about. Okay? One 3-bisphosphoglycerate. What makes it a high energy molecule?
Phosphocarbon anhydride bond? The mixed one.
Which one of these phosphates is the high energy one? Left or right?
Right.
My left or your left?
Your left. Now.
When I face this way or that way?
When facing
This one or that one?
To the right of the
This
screen.
one.
There you go.
What's this one? What kind of linkage is that?
An ester.
An ester. What kind of linkage is that? All right, there's our mixed anhydride. So 1,3-bisphosphoglycerate. Where do we find 1,3-bisphosphoglycerate?
Glycolysis.
Yeah. It's an intermediate in glycolysis. And it is the first intermediate in glycolysis that is high enough energy that we can create ATP out of it. Right? We can use this as a molecule to make ATP. So, mixed anhydride, right, with another phosphate on there. Not much opportunity for resonance. So, acetyl phosphate, right, very similar, right, still a mixed anhydride, right, if we go back. Right. Those two are fairly close together. But 1,3-bisphosphoglycerate,
Why is it that ATP is in between those two?
Well, note ATP is in two places on the right. This is the one where we're getting AMP and the pyrophosphate. And this is the one where we're getting ADP and a simple phosphate. Why is this one higher energy than this one would be another question.
I thought they were opposite.
Wouldn't it?
When I was doing it, like thinking about it, I thought the opposite, but.
Is that
Would-
because of the enzyme that you were talking about that turns that back into ATP?
No, that's just considering this hydrolysis, because this is considered separately.
So it's not including the PP?
No, it's not including the hydrolysis of the pyrophosphate.
Is it because with the monophosphate, then there's not as much charge density?
Yeah, I would guess that that it's breaking up the charge density, and then you're getting resonance stabilization of you're getting more resonance stabilization of the pyrophosphate here than you can get here, right? The question is, where are the two phosphates? I would guess that there's more resonance stabilization of all that negative charge here than here. Actually, if we think about it, if we draw it out, there's one more oxygen participating in the resonance here versus here. Right? The ester oxygen can't participate as cleanly in the resonance as the free oxygen can here. So the negative charges are distributed among more oxygen atoms here than here. It's the best explanation I can come up with. Why didn't you ask me that question yesterday, Kyle, so I could think about it overnight? I'd come up with a better answer than that. Okay? Does that make sense? I mean,
Oh wait, which one?
really all we're doing is trying to use our chemistry to justify these numbers that biologists have been telling us forever. Can we come up with reasonable arguments for why this stuff makes sense? Because the better these things make sense, the more we can make qualitative predictions if this isn't sitting in front of us. Right? That's what we're trying to do. Gee, that looks like it might go that way. Okay. Makes you sound good in meetings and stuff.
Looks like it might be on the exam. I have a question for the two that are, if they're both mixed anhydrides, how would you know that one is?